don't feel like doing this shit, but we gotta do it. Come on.
Let's say we are tasked with testing the security of an online shopping web application. Many questions pop up. Can we reuse a single $10 gift card to pay for a $100 item? Can we apply the same discount to our shopping cart multiple times?
Huh.
The answer is maybe. If the system is susceptible to a race condition vulnerability, we can do all this and more.
Okay.
This room introduces the race conditions vulnerability. A race condition is a situation in computer programs where the timing of events influences the behavior and outcome of the program. It typically happens when a variable gets accessed and modified by multiple threads. Due to a lack of proper lock mechanisms and synchronization between the different threads, an attacker might abuse the system and apply a discount multiple times or make money transactions beyond their balance. Learning objectives. After completing this room, you will learn about the following: race conditions vulnerability, using burp suite repeater to exploit race conditions along the way. You will also learn about threads and multi-threading state diagrams. Learning prerequisites to follow this room. We recommend familiarity with the HTTP.
Fuck, that's long as hell.
In this task, we will provide a quick overview of the following terms: program, process, thread. Multi-threading programs. A program is a set of instructions to achieve a specific task. You need to execute the program to accomplish what you want.
Okay.
Unless you execute it, it won't do anything and remains a set of static instructions. Think of it as a recipe. You just downloaded a new coffee recipe that includes a variety of herbs, such as cardamom and cinnamon.
What the hell is a cardamom?
These are the instructions.
Never heard of cardamom.
Unless someone carries out the above instructions, no coffee will be served.
Okay.
Compare this to our minimal Flask, Python, hello, world, server. The code below dictates that the app will listen on port 8080 and respond with a minimal greeting HTML page that contains hello, world. However, we must run these instructions, program, before we expect to get any greeting pages. Please note that the Flask code below is shown for demonstrative purposes only. We didn't provide an environment to run it as it is outside the scope of this room.
From Flask, import Flask. I don't know what Flask code is. Oh, it's Python. It just said that. Fuck. Oh. Oh, my fucking back, boy.
Processes one afternoon.
Well, my my cat.
You decide to try out this new coffee recipe you downloaded online. You start going through the recipe one step at a time. You are in the process of making this coffee recipe. While in the process of executing the instructions, you might get interrupted by an urgent call. Or you might work on another job while waiting for the water to heat. Interruptions and waiting are generally unavoidable. The act of carrying out the recipe instructions to make coffee is similar to the process of executing program instructions. A process is a program in execution. In some literature, you might come across the term job. Both terms refer to the same thing, although the term process has superseded the term job. Unlike a program, which is static, a process is a dynamic entity. It holds several key aspects, in particular, program, the executable code related to the process memory, temporary data storage state. A process usually hops between different states. After it is in the new state, i.e., just created, it moves to the ready state, i.e., ready to run once given CPU time. Once the CPU allocates time for it, it goes to the running state. Furthermore, it can be in the waiting state pending I/O or event completion. Once it exits, it moves to the terminated state.
Fuck. Oh. Let me out of it. Oh.
If you run the Flask code above, a process will be created, and it will listen for incoming connections at port 8080. In other words, it will spend most of its time in the waiting state. When it receives an HTTP GET/request, it will switch to the ready state, waiting for its turn to run based on the CPU scheduling. Once in the running state, it sends the HTML page to the client and returns to the waiting state. From the server's perspective, the app is servicing clients sequentially, i.e., client requests are processed one at a time. Note that Flask is multi-threaded by default since version 1.0. We used the argument without threads to force it to run single-threaded. Please note that the Flask command shown below is for demonstrative purposes only. Let's wrap up with another coffee analogy. Consider the case of a commercial espresso machine in a coffee shop. Let's say it has two portafilters. At the start of the workday, the barista turns on the espresso machine, and whenever a customer orders an espresso, one portafilter is used to prepare an espresso shot for them. Does another customer order an espresso? No problem, the second portafilter to the rescue. The warmed-up espresso machine is the process, each new order is assigned a portafilter, that's the analogy for the thread. A thread is a lightweight unit of execution. It shares various memory parts and instructions with the process. In many cases, we need to replicate the same process repeatedly. Think of a web server serving thousands of users the same page, or a personalized page. We can adopt one of two main approaches: serial, one process is running, it serves one user after the other sequentially. New users are in queue. Parallel, one process is running, it creates a thread to serve every new user. New users are only in queue after the maximum number of running threads is reached. The previous app can run with 4 threads using Gunicorn. Gunicorn, also called the green unicorn, is a race conditions.
I'm tired,
Premium
man.
room. Learn about race.
I forgot.
The previous app can run with 4 threads using Gunicorn. Gunicorn, also called the Green Unicorn, is a Python WSGI HTTP server. WSGI stands for Web Server Gateway Interface, which bridges web servers and Python web applications. In particular, Gunicorn can spawn multiple worker processes to handle incoming.
Um,
It's time.
Real-world analogy. Picture the following situation. You call a restaurant to reserve a table for a crucial business lunch. You are familiar with the restaurant and its setup. One particular table, number 17, is your preferred choice, considering it has a nice view and is relatively isolated. You call to make a reservation for table 17, the host confirms it is free as no reserved tag is placed on it. At the same time, another customer is talking with another host and making a reservation for the same table.
who really reserved the table? Yeah, that's a good gosh darn question.
Who really reserved the table? Who really reserved the table? That's a race condition. Why did this happen? This unlucky situation happened because more than one host was taking reservations. Furthermore, it took the host a few minutes to fetch the reserved tag and put it on the table after updating the daily reservation book. There is at least a 1-minute window for another client to reserve a reserved table. Similarly, when one thread checks a value to perform an action, another thread might change that value before the action takes place. Example A. Let's consider this scenario. A bank account has $100. Two threads try to withdraw money at the same time. Thread 1 checks the balance, sees $100, and withdraws $45. Before thread 1 updates the balance, thread 2 also checks the balance, incorrectly sees $100, and withdraws $35. We cannot.
It's 35 plus.
Be 100% certain which thread will get to update the remaining balance first. However, let's assume that it is thread 1. Thread 1 will set the remaining balance to $55. Afterwards, thread 2 might set the remaining balance to $65 if not appropriately handled. Thread 2 calculated that $65 should remain in the account after the withdrawal because the balance was $100 when thread 2 checked it. In other words, the user made 2 withdrawals, but the account balance was deducted only for the second one because thread 2 said so. Example B. Let's consider another scenario. A bank account has $75. Two threads try to withdraw money at the same time. Thread 1 checks the balance, sees $75, and withdraws $50. Before thread 1 updates the balance, thread 2 checks the balance, incorrectly sees $75, and withdraws $50. Thread 2 will proceed with the withdrawal, although such a transaction should have been declined. Examples A and B demonstrate a time of check to time of use, talk to, vulnerability. Example code. Consider the following Python code with 2 threads simulating a task completion by 10% increments. These 2 threads start together, they do nothing except print a value on the screen. Consequently, one would expect them to finish simultaneously, or at least the result to be consistent. However, in the program above, there is no guarantee which thread will finish first and how early it will be. Below is the first execution output.
Let's do that real quick.
Running this program multiple times will lead to different results. In the first attempt, thread 2 reached 100 first, however, in the second attempt, thread 2 reached 100 second. We have no control over the output. If the security of our application relies on one thread finishing before the other, then we need to set mechanisms in place to ensure proper protection. Consider the following 2 examples to better understand the bug's gravity when we leave things to chance. On the attack box, you can save the above Python code and run it multiple times to observe the outcome. For instance, if you saved it as race.py, you can run the script using the python race.py command.
Fuck, how did I forget how to do that? I forgot how to make text. That's what I thought, man. Alright, where did it save that? In the root? Yeah, I knew there was an error right there. Whatever.
Causes: as we saw in the last program, two threads were changing the same variable. Whenever the thread was given CPU time, it rushed to increase x by 1. Consequently, these two threads were racing to increment the same variable. This program shows a straightforward example happening on a single host. Generally speaking, a common cause of race conditions lies in shared resources. For example, when multiple threads concurrently access and modify the same shared data. Examples of shared data are a database record and an in-memory data structure. There are many subtle causes, but we will mention three common ones: parallel execution, web servers may execute multiple requests in parallel to handle concurrent user interactions. If these requests access and modify shared resources or application states without proper synchronization, it can lead to race conditions and unexpected behavior. Database operations. Concurrent database operations, such as read, modify, write sequences, can introduce race conditions. For example, two users attempting to update the same record simultaneously may result in inconsistent data or conflicts. The solution lies in enforcing proper locking mechanisms and transaction isolation. Third-party libraries and services. Nowadays, web applications often integrate with third-party libraries, APIs, and other services. If these external components are not designed to handle concurrent access properly, race conditions may occur when multiple requests or operations interact with them simultaneously. Let's visit web application architecture to explain how race conditions are possible. Client-server model. Web applications follow a client-server model. Client. The client is the program or application that initiates the request for a service. For example, when we browse a web page, our web browser requests the web page file from a web server. Server. The server is the program or system that provides these services in response to incoming requests. For instance, the web server responds to an incoming HTTP GET request and sends an HTML page, or file, to the requesting web browser, client. Generally speaking, The client-server model.
Fuck.
Web applications follow a client-server model. Client. The client is the program or application that initiates the request for a service. For example, when we browse a web page, our web browser requests the web page file from a web server. Server. The server is the program or system that provides these services in response to incoming requests. For instance, the web server responds to an incoming HTTP GET request and sends an HTML page, or file, to the requesting web browser, client. Generally speaking, the client-server model runs over a network. The client sends its request over the network, and the server receives it and processes it before sending back the required resource. Typical web application. A web application follows a multi-tier architecture. Such architecture separates the application logic into different layers or tiers. The most common design uses 3 tiers. Presentation tier. In web applications, this tier consists of the web browser on the client side. The web browser renders the HTML, CSS, and JavaScript code. Application tier. This tier contains the web application's business logic and functionality. It receives client requests, processes them, and interacts with the data tier. It is implemented using server-side programming languages such as Node.js and PHP, among many others. Data tier. This tier is responsible for storing and manipulating the application data. Typical database operations include creating, updating, deleting, and searching existing records. It is usually achieved using a database management system, DBMS. Examples of DBMS include MySQL and PostgreSQL. States. Let's visit some examples from business logic before diving deeper. We will consider the following examples: validating and conducting money transfer, validating coupon codes and applying discounts, validating and conducting money transfer. Consider the example of transferring money to a friend or your other account. The program will progress as follows. The user clicks on the Confirm Transfer button. The application queries the database to confirm that the account balance can cover the transfer amount. The database responds to the query if the amount is within the account limits. The application conducts the transaction if the amount is beyond the account limits. The application shows an error message. Validating coupon codes and applying discounts. Let's consider the example of applying a discount coupon. The user goes to their shopping cart and adds a coupon to get a discount. The steps might be something along the following lines. The user enters a coupon code. The application queries the database to determine whether the coupon code is valid and whether any constraints exist. The database responds with validity and constraints. The discount is applied if the code is valid and there are no constraints on applying it for this user. An error message is displayed if the code is invalid or there are constraints on applying it for this user. Two states. Think again. Let's continue our analysis of applying a discount coupon. Ideally, we expect 2 states, coupon not applied and coupon applied. However, this is too simplistic to depict real sophisticated scenarios. We can add an intermediary state, checking coupon applicability. Depending on how the application is developed, we can expect more states. For example, Checking coupon applicability might involve two states: checking coupon validity and checking coupon constraints. A coupon might be valid, but existing constraints prevent it from being applied. Similarly, coupon applied might be divided into two states, one of which is recalculating total.
Chickens sleep in trees. That must be hard to do.
Depending on how the application is developed, we can expect more states. For example, checking coupon applicability might involve two states: checking coupon validity and checking coupon constraints. A coupon might be valid, but existing constraints prevent it from being applied. Similarly, coupon applied might be divided into two states, one of which is recalculating total. Why is this important for race conditions?
Yeah.
In the state diagram above, we can see that we pass through multiple states before the coupon is marked as applied. Let's draw the states on a time axis, as shown below. There is a time window between the instant we try to add a coupon and the instant where the coupon is marked as applied and cannot be applied again. As long as the coupon is not marked as applied, most likely, no controls prevent it from being accepted repeatedly. We might be able to apply it multiple times during this time window. This situation is similar when considering the states for the program making a money transfer. Although ideally speaking, it would be two states, considering the business logic, we can easily update the diagram to include three states. The reason is that we expect some time spent checking the account balance and limits. Although this amount of time might be brief, it is not zero. If we dig deeper, we can uncover more hidden states. However, even if the web application is vulnerable, we still have one challenge to overcome: timing.
Yeah, that's what I'm saying.
Even in vulnerable applications, this window of opportunity is relatively short. Therefore, exploiting it necessitates that our requests reach the server simultaneously. In practice, we aim to get our repeated requests to reach the server only milliseconds apart. How can we get our duplicated requests to reach the server within this short window? We need a tool such as Burp Suite.
Wow, how many days is it? I don't know. 3? Alright, we'll do this tomorrow. It's late. I'm tired.